Hi folks, in this video we're going to talk about Millikan's oil drop experiment. Now he did this experiment in 1909 with the aim of trying to determine the fundamental unit of charge. Now we know that the fundamental unit of charge is the charge of an electron, or indeed the charge of a proton, which is 1.6 times 10 to the minus 19 coulombs. And until he did this experiment, it was unknown. And so here we have in the course notes Millikan's oil drop experiment on page 15, and and I'll just take you through the experimental setup and the and his findings and how you would calculate this in a question. So Millikan's oil drop experiment, I'm going to quickly sketch it out, and to save boring you, so he started with what we would call an oil atomizer, and so he took some oil and he sprayed it out through a nozzle, and what that did, it created a very fine mist of oil, and so there's some tiny oil droplets there. And what would happen is that the droplets of oil would start to accelerate downwards, but very quickly the drops would reach terminal velocity. And although we don't need to get into it, but basically through knowing the rate at which they're falling, or the terminal velocity that they reach, we can determine their mass. So what they would do, they would make this very fine mist of oil, and then they would pick an oil drop, and they would observe that oil drop, and you may have like some sort of scale that you can see, and if you know the distance of this, and then you know how long it takes to cover that distance, then you can work out how fast it's falling. You can determine its terminal velocity, and through terminal velocity then you can work out the mass of the oil drop. So we know its mass. Then they would have, sorry, excuse me a wee second. So they would then have these parallel plates, and these plates would be charged up. We would know the separation of the plates. That's something that we can control, so we can fix the separation of the plates, and there is a potential difference applied across these plates. But what they did is they drilled a small hole in the top of one of these plates. So if we're looking at it from top down, you have your fixed plate, and then you'll drill a small hole in it. And what you're trying to do is you're trying to just allow single oil drops really to just fall straight through. And so we have this oil drop here, and we've picked this oil drop, and we've measured its terminal velocity, and so now we know its mass, and so it's falling its terminal velocity, and if we know what its mass is, we can figure out the weight that's acting on it. Now this would be balanced by frictional forces from the air, but we're not going to worry too much about that, because what we're actually going to do, so we know the size of the weight, and what we can do is we can, let me get something else. So we can take and so he fired X-rays into this chamber, and by firing the X-rays through there, he would give the oil drops a charge. Now we don't know what this charge is, but some of them would become positive charges, some of them would become well, positively charged droplets, some would become negatively charged droplets. I mean, but we don't know what that is. But anyway, so we're focusing on a droplet, and let's just assume for a second that this drop that we're fired through has become now negatively charged. So negative, and it will have a charge of Q. Okay, and what we can do is we can take this now negatively charged oil drop that's falling at a constant velocity, and we can adjust the voltage across the plates. And what we're trying to do is falling down, and we adjust the voltage of the constant plates. We're observing this tiny oil drop. We can look at it through a traveling microscope. Observe this oil drop, and we can adjust the voltage. We can increase it until we get it to be stationary. Now, if it's stationary, the point at which it's going to be stationary is when the forces are balanced. And so we'll slow it down, it'll eventually stop, and when it's stopped and when it's held stationary, the force of gravity is going to be acting downwards, and then there's going to be the force due to the electric field. So the force due to the electric field is going to be acting in an equal and opposite direction in order to hold it stationary. And the force from the electric field, so force electric, we know is QE, where Q is the charge in the oil drop and E is the electric field strength that's created from this. And how do we know what the electric field strength? Well, E is voltage over distance, so the voltage that we set in the distance of the plate separation. So putting that all together, we can have the force from the electric field is going to be, substitute this for E, we're going to have QV over D. Now when it's stationary, this is going to equal the weight, use mg. And putting this all together, we'll have QV over D is equal to mg. Now we know the voltage, we know the distance, we know the mass of the oil drop from its terminal velocity, and we know gravitational field strength. The only unknown in this then is Q, which we can determine. Now when Millikan did this experiment, he got numerous readings. He did thousands and thousands of tests of this, and I'm going to put up some sample results. So he would have Q coulombs, and he had 1.6 times. And we could go on and on and on. No matter what he did, and you could also, I might add, is swap the polarity of the plates. So you could put positive down here, negative down here, and instead of having negative numbers, you would have a quantity of charge of positive numbers. Of course, if it became positively charged here, it's because it would have lost electrons in the X-rays, or it would have, if it's negative, it would have gained electrons in the X-rays. But no matter what he did, he always found that the amount of charge that was calculated from this, if we just rearrange this, so we would have mgd over v. So no matter what he did with this, he would always get an integer multiple of this number here. So it would always an integer, always an integer multiple of 1.6 times 10 to the minus 19 coulombs. And so he said that, well, that must be the smallest possible charge that you can have. And it's sometimes called the fundamental unit of charge. So, and this is what we have now today, that the smallest amount of charge that you can have is going to be 1.6 times 10 to the minus 19. Now I know that we have since this was done, we've discovered the existence of quarks, and they would have, or they could have either plus or minus 1/3 or plus or minus 2/3 of the unit of charge. But the fact is that these quarks do not ever exist on their own, and they will always combine to form an integer unit of that same multiple, 1.6 times 10 to the minus 19. So we would say that yes, the smallest unit of charge that you can have is 1.6 times 10 to the minus 19 coulombs. Okay, so we'll now look at a worked example. In this worked example, we have parallel plates with a separation of 20 millimeters. There's a potential difference of 2000 volts, which is used to keep the oil drop stationary. And we've calculated that the mass of the oil drop is 4.9 times 10 to the minus 15 kilograms. And what we're going to try and do is determine the charge on the oil drop, and hence calculate the number of excess electrons. Now, because it's being held in the orientation of the plates here, we know that the Q must be negative. So Q is negative. If the plates were around the other way, we would know that the Q would have to be positive. But because it's being held like this, it has a number of excess electrons, and rather than missing some electrons. So what we'll say, first of all, is that the force due to gravity is going to be equal to the force due to gravity is going to equal the force from the electric field, and the force of gravity would be mg, which is going to equal to QE, but also E is equal to E over D. And so putting all this together, we could have mg is equal to QV over D, and rearranging for Q, our Q is equal to mgd all over V. Substitute in our values, so mass 4.9 times 10 to the minus 15 times gravitational field strength 9.8 times plate separation, which was 20 millimeters, so it would be 0.02, and all over our voltage, which is 2 kilovolts, 2000 volts, and that will equal 4.8 times 10 to the minus 19. 4.8 times 10 to the minus 19 coulombs. So the charge on that oil drop would be 4.9 times 10 to the minus 18 coulombs. And from that, we would then say Number of excess electrons would be 4.8 times 10 to the minus 19 divided by the fundamental unit of charge, which would be 1.6 times 10 to the minus 19, and that will of course give us 3 electrons. Okay, and that's it. That's Millikan's oil drop experiment. Okay, thanks for watching. Bye-bye.